Hey there, Stuffology fans. Before diving into today's wild ride through the cosmos, just a quick nudge to hit that subscribe button wherever you're listening. It helps us keep bringing you these deep dives into the stuff that makes the universe tick. All right, let's talk about something that's been sparking curiosity for decades: the Drake equation. It's a formula that tries to estimate how many alien civilizations might be out there capable of chatting with us across the stars. This isn't just sci fi daydreaming, it's a serious attempt to quantify the unknown, and it all started with a guy named Frank Drake. Back in 1961, Frank Drake, an astronomer with a knack for big questions, was at the Green Bank Observatory in West Virginia. He wasn't just stargazing, he was thinking about life beyond Earth. The search for extraterrestrial intelligence, or SETI, was just kicking off, and Drake wanted a way to frame the conversation. He came up with this equation that's less about giving a final answer and more about breaking down the problem into manageable chunks. It's like trying to guess how many fish are in the ocean. You start with what you know and work from there. The equation itself looks simple but hides a ton of complexity. N equals R star times FB times NE times FL times FI times FC times L. Each term is a piece of the puzzle. N is the number of communicative civilizations in our galaxy. R star is the rate at which stars form. FB is the fraction of those stars with planets. NE is the number of planets per star that could support life. FL is the fraction where life actually appears. Fi is where intelligent life evolves. FC is the fraction of those that develop tech to send signals. And L is how long those civilizations last. Sounds straightforward, right? But every term is a guess, and that's where the fun and the debates begin. Drake's equation wasn't born in a vacuum. The early 1960s were a heady time for space exploration. Sputnik had already shocked the world, and the idea of life on Mars or beyond wasn't just for pulp magazines anymore. Scientists were starting to take the question seriously, and Drake's work gave them a framework. He presented it at a small conference in Green Bank, with just a dozen or so big brains in the room, including Carl Sagan, who'd later make cosmos-level questions a household topic. They weren't solving the equation. They were using it to map out what we don't know. It was a bold move to put numbers on something so speculative, but that's what made it revolutionary. Let's break down those terms a bit. R star, the star formation rate, was something astronomers could estimate even back then. In our galaxy, the Milky Way, we're talking about a few new stars per year. Not too controversial. FP, the fraction of stars with planets, was trickier in 1961. Exoplanets weren't confirmed until the 1990s, so Drake and his colleagues were going on educated guesses. Today, thanks to telescopes like Kepler, we know planets are everywhere. Most stars have at least one. That bumped up the odds of alien life considerably since Drake's time. Now, NE, the number of potentially habitable planets per star, is where things get juicy. Back then, habitable meant Earth-like, rocky, not too hot, not too cold with liquid water. The Goldilocks zone, basically. Scientists figured maybe 1 in 10 stars might have a planet like that. Today, we've found thousands of exoplanets, and the number keeps climbing. Some estimates suggest 1 in 5 stars might have a habitable world. But habitable doesn't mean inhabited, and that's where the next terms come in. FL, the fraction of planets where life actually emerges, is a total shot in the dark. On Earth, life popped up pretty fast, within a billion years of the planet forming. But is that normal? We've got no other examples to work with. Some scientists think life is inevitable given the right conditions. Others say Earth might be a fluke. Then there's Fi, the fraction where intelligent life evolves. Think about Earth. It took 4.5 billion years to get from single-celled goo to creatures building radios. Dinosaurs ruled for millions of years without inventing Wi-Fi. Intelligence isn't guaranteed. FC, the fraction of intelligent species that develop communication tech, is another hurdle. Maybe intelligent aliens exist, but never get past stone tools. Or maybe they do, but their signals are too weak, or they're using tech we can't detect, like neutrinos or something wild. Finally, L, the lifespan of a communicative civilization, is the real kicker. Humans have been broadcasting radio waves for about a century. Will we last another 100 years? 1,000? If civilizations self-destruct quickly, that shrinks the odds of us overlapping with them in time. What's wild about the Drake equation is how it forces you to confront these unknowns. When Drake first proposed it, he plugged in some optimistic numbers and got a result suggesting maybe 10 communicative civilizations in the galaxy. Others have crunched the numbers and gotten anywhere from one, us, to millions. It depends on your assumptions. Optimists see a galaxy teeming with life. Pessimists think we might be alone. The equation doesn't solve the mystery. It just sharpens the questions. By the late 1960s, the equation was a cornerstone of SETI. It guided projects like Drake's own Project Ozma, where he used the Green Bank telescope to listen for signals from nearby stars. No luck, but it was a start. Over the decades, SETI grew, with bigger telescopes and better tech, all inspired by that original framework. The equation also caught the public's imagination, thanks to folks like Sagan, who used it to explain why searching for aliens was worth doing. It wasn't just about finding ET. It was about understanding our place in the universe. Fast forward to today, and the Drake equation is still relevant, but we've got more data to play with. Exoplanet discoveries have exploded, giving us a better handle on FB and NE. We've also learned more about extreme life on Earth, microbes in boiling vents or frozen Antarctic ice, which expands what habitable might mean. But the later terms, like Fi and L, remain maddeningly speculative. Some argue we need to factor in new variables, like the odds of a planet having a stable climate or avoiding cosmic catastrophes like asteroid impacts. The equation's legacy isn't in giving us a number. It's in sparking a conversation that's lasted over half a century. It's influenced everything from NASA's astrobiology programs to movies like Contact. It's why we keep building bigger telescopes, like the James Webb, and sending probes to Mars, looking for signs of ancient life. It's also why SETI hasn't given up, even after decades of silence. The equation reminds us that the search isn't just about aliens. It's about understanding life's potential. One fascinating angle is how the equation has shaped debates about our own future. That L term, the lifespan of civilizations, hits hard. Are we doomed to crash and burn, or can we beat the odds? Some scientists use the equation to argue for sustainability. Civilizations that last longer increase the odds of contact. Others see it as a warning. If we're not careful, we might join the list of short-lived species, broadcasting for a cosmic blink before fading out. The Drake equation also bridges science and philosophy. It asks us to think about what intelligence means, what communication looks like, and whether we're even asking the right questions. Maybe aliens don't use radio waves. Maybe they're AI or hive minds or something we can't imagine. The equation doesn't account for that, but it gets us talking. It's a tool for curiosity, not a crystal ball. Today, the equation remains a touchstone for anyone pondering life in the cosmos. It's taught in classrooms, debated at conferences, and scribbled on whiteboards by astronomers dreaming of first contact. Frank Drake, who passed away in 2022, left behind a question that's bigger than any answer. His equation isn't about certainty, it's about possibility. It's a reminder that the universe is vast, and we're just starting to explore it. So where does that leave us? Still listening, still searching, still wondering. The Drake equation doesn't promise we'll find aliens tomorrow, but it keeps us looking up. It's a map for navigating the unknown, and in a way, that's its greatest gift. It tells us that the search for life is as much about who we are as it is about who's out there.